Continuing in 2.3, more on linear transformations. So here's the definition again of a linear transformation. And these are for just standard vectors in Rn or Rm. So here's the definition. If you sum two vectors in Rn, is it the same thing as doing the transformation and just summing those two vectors in Rm? And then this one is scalar multiple. Can you basically factor it out of the function? And we showed a couple examples that work and don't work. It preserves linear combinations. That comes into some proofs and stuff later. Square roots was pretty clear. You can't separate it. It's not linear. We call that linear if you can do this transformation. Natural log, if you add 2, of course that doesn't work. And then we defined this one, R2 to R, where you're just summing the 2 in the middle. So is this a linear transformation? So we showed that it was a linear transformation. So yes, so therefore T is a linear transformation. Okay, so next couple questions then. Let's suppose T is a linear transformation. And the question is, does 0 map to 0? So 0 in R, and let me change that. That's supposed to be N to M. Does the 0 vector in Rn, sometimes they put a subscript like that, map to the 0 vector in Rm? And so we could actually investigate that. Does that happen every time? All right, so basically, to make this shorter, it does. So the 0 vector maps to the 0 vector every time. All right, so yeah, we'll just put it like that. That's fine. So yes, always. Let's look at a little proof of that. So the 0 vector in linear transformation always maps to 0 vector. Does that make sense? Like, why would that make sense? So let's assume this is a linear transformation. And if you look at T of 0, that's equal to T of, that's a 0 vector. So this 0 vector here is in Rn. So you can put a little in there. But that is always equal to the number 0 times the 0 vector. And because it's a linear transformation, we can take out the 0, the number 0, times T of the 0 vector. And that's going to be equal to this. Anything times this 0 vector is going to be 0. So this, just to be maybe hopefully more clear, this is in N here. This is still in N. But then when you do the transformation, you're going to get 0 times the 0 vector in M, which is, of course, just the 0 vector in M. But that'll be true regardless of whatever's here, because this is always true. So the conclusion is, therefore, 0 vector, so maybe I should say it like that, the 0 vector, therefore there's only one, right? The 0 vector in Rn maps to the 0 vector in Rm, like whatever the transformation is for the vectors. So that's always true. Right, because remember, this transformation has to be true for all R. So if R is equal to 0, this is what you will always get. So you can't get it like another one. Okay. Actually, we will talk about if zero mapping to zero, and if it maps back, then that's a one-to-one function. If it maps to a whole set that gives you zeros, then this is called the kernel over here. We'll get to more of that in chapter 3. So forget I said anything so far. We'll get that later. But we're going to not do every little detail in 2-3 and save it to the more general cases in chapter 3 on vector spaces. So one way to picture that then for a mapping, made a decent circle, didn't it? Is like this. Duplicate. So we always have then that 0 here in N maps to 0 over here in a transformation. Okay, now, and so the point too of all this is that this is something we can check. Okay, so this is something we can check to determine if a mapping is a linear transformation. So in other words, if t of the zero vector does not equal the zero vector in the other set, right? Then the function t is not a linear transformation. It's a function, but it's not a transformation, a linear transformation. So it all has to do with that r being factored out. It has to be true for every r. So if r is 0, it will go to 0, period. Okay, here's another example. Let's determine if this is a linear transformation. And then we'll do another example for matrices and stuff. So for this one, just wanted to hit one more for what we did above. Determine if this function, t from R2 to R, defined as such, is a linear transformation. And so you have the vector xy in R2, and then you take those two components when you do the transformation, you subtract them and then add 1. So is that a linear transformation? Is the question. And so you can start checking what you need to check. So the goal is to show or determine, and this is something you write down, have in your mind what you're doing. You got to show if the sum of those two is equal to, so t of u plus v, is that t of u plus t of v. So is that true? So you got to show that. And then you'd have to show t of ru, is that equal to r of t of u? Okay, so, and I'm writing that down just to kind of like remind us that that's what we're doing. I'm going to try to highlight this thing. Yeah, pretty good. It's like if I make it bad enough, it puts a box around it. So that's show or determine. Now, we can start doing this. Let's try number 1. And so when you do this, you want to be careful about where your u and v are, because it has to be true for every case. So what you do is you'll say you may want to mess around, just scratch work on your own. I'll try to do it a little more carefully to show you, but you put those vectors arbitrarily in R2. So then you'll end up with, I'll just write it. So then U is U1, U2, and your V is V1, V2. That's how you'd want to write it. That helps picture what that sum means. It's the sum of those two vectors is what we're doing. So for 1, you're doing T of your U plus V. So that's T, and then let's go and put those in as vectors. U1, U2 plus V1, V2. So that's the sum of those two inside the transformation, inside the function. And so you do that. So you say that's T of, now add them up inside the function. So you just get, because it's defined to be, when you define this stuff, this is what you're showing works, but this is the definition. You have just one vector in there. So we need to combine this together to get one vector. That's always the case. Okay, so I don't know, maybe I'll put that down. We need one vector inside. So we need one vector. I'll just say that. Just give you an idea. And so you get U1, so here's your vector, U1 plus V1, comma, U2 plus V2 is what you end up getting. All right, so then now you operate on those two things, your X and your Y. So you're going to subtract them and then add 1. So that's equal to U1 plus V1 minus quantity U2 plus V2, and then you're going to say plus 1. Okay, then you simplify that and see what you get. So that's U1 minus U2 plus V1 minus V2 plus 1. So is that, can you make that equal to T of U plus T of V? So T of U is U minus V plus 1, right? So you could kind of work backwards a little bit and see what's happening. Let's just do that. So if you work backwards, T of U1 is U1 minus U2 plus 1. And then T of V is V1 minus V2 plus 1. So in that case, you get, so this part's the same, right? This right here is what you want. But if you do this transformation for each case, you're going to get a plus 2. And so we can't, so you get basic, so I mean, you could write that out. It's pretty clear now. U1 minus U2 plus V1 minus V2, but then you get plus 2. These are not equal. So therefore not a linear transformation. Okay, so therefore T is not a linear transformation. Now, that was like the tough way to do it. I just mentioned up here about 0 to 0. We could just check to see if 0 maps to 0. Okay, so let's just do that. So we may check to see if 0 maps to 0. And so by doing that, you're really just going to be t of the 0 vector. Let me write it out nicely like you would show it. You do t of the 0 vector, which is t of, in this case, 0, comma 0, which is going to be that transformation by definition of the function is 0 minus 0 plus 1. Well, that is not equal to the 0 vector. And so same conclusion, because 0 does not map to 0. Therefore, not a linear transformation. Okay, so again, another one that's not a transformation. Let's do one that is. And then we'll do, we'll stop here. Then we'll do, we'll wrap it up.